Hello everyone. Today we're going to talk about tonicity and osmolarity. Fluids found inside of your cells, we refer to it as intracellular fluid, and fluid outside of our cells, we refer to it as extracellular fluid. That could include the fluid found in between the cells, known as interstitial fluid, or the fluid found in the blood, known as the plasma. The condition inside of our cell versus outside is not identical. And there are three important ions to know their relative concentration inside versus outside. And those are sodium, potassium, and chloride. If we take a look at this image right here, this is the intracellular fluid. And right here is the extracellular fluid. Whether we're talking about the interstitial fluid or whether we're talking about the plasma. You would notice that the sodium concentration is much higher in the extracellular fluid compared to intracellular fluid. Another ion that we're going to talk about is the chloride ions. You would notice that the chloride ion is much higher in the extracellular fluid compared to the intracellular fluid. So sodium and chloride ions are much higher in the ECF compared to the ICF, the intracellular fluid. The intracellular fluid has a higher concentration of the potassium ions compared to the potassium ions found in the extracellular fluid. Osmosis is the movement of water. Water moves to dilute the more concentrated solution. So water likes to move from a high water concentration to a low water concentration area. Or you can think of it as the movement from the low solute concentration to the high solute concentration. So if we take a look at this image right here, there are two sides, A and B, separated by a semi-permeable membrane. And let's assume that the semi-permeable membrane only allows water to pass through and not the solutes. You would notice that side A has a lower solute concentration compared to side B. If side A has the lower solute concentration, that means that side A has the higher water concentration. And so the water is going to start moving from side A to side B. And so you can see the water moving to side B, and the volume on side B is getting higher. Now, the water is going to keep moving from side A to side B until equilibrium is reached. The force applied to oppose that osmosis is known as the osmotic pressure. Two terms that we need to talk about are molarity and osmolarity. Molarity is a term used to refer to the concentration of a solution in terms of moles per liter or millimoles per liter. Osmolarity, on the other hand, expresses the total number of particles in a solution. And the units would be osmoles. So you can say osmoles per liter, or you can say milliosmoles. What does it mean, the number of active particles in a solution? There are inorganic salts, such as sodium chloride, potassium chloride, calcium chloride. Those inorganic solutes usually dissociate in the fluid, so they break down. So for example, if we have sodium chloride, an inorganic salt, it's going to dissociate, it's going to break down into a sodium ion and a chloride ion. That's two particles right there. Calcium chloride, when it's added into water, it dissociates into a calcium ion and two chloride ions. That's a total of 3 particles. So let's say that you have a solution and that solution contains 2 millimoles of sodium chloride, and you want to figure out the osmolarity for that solution. So what you would do is take the 2 millimoles of that sodium chloride and you have to multiply it by the number of particles. Since sodium chloride dissociates into 2 particles, you're going to multiply by 2. So the concentration in terms of osmolarity for that solution would be 4 milliosmoles. Another example, let's say you have 2 millimoles of calcium chloride. You're going to multiply this time by 3 because we know calcium chloride dissociates into 3 particles. So you would get 6 milliosmoles. Now, there are organic molecules like glucose, or we can refer to it as dextrose, and those organic molecules like sugar, what's another example? For example, we have proteins. Those do not dissociate. So if you have 1 millimole of glucose, you would just multiply by 1 because glucose is not going to dissociate into ions. And so if you have 1 millimole of glucose, you end up with 1 milliosmole of glucose. If you have 2 millimoles of glucose, you would still have 2 milliosmoles of glucose. The normal osmolarity of our cells or of our human body, whether we're talking about intracellular or extracellular fluid, it ranges from about 280 to 296 milliosmoles per liter. And just for abbreviation, this is how we would write it, milliosmoles right there. The range differs. So some say it's from 280 to 340. Some say it's from like 250 to 300. So to simplify things, we're just going to round it to 300. Okay, so we're just going to go with 300 milliosmoles. And so the osmolarity tells you the total number of particles, but it doesn't tell you what's going to happen to the cell if it was placed to a solution. It doesn't tell you whether your cell is going to gain or lose water. It doesn't give you that information. Osmolarity just tells you the total number of particles inside versus outside your cells. So let's take a look at this table right here to compare the osmolarity of certain solutions. Let's say that you have solution A, B, and C. And the osmolarity of solution A is 1 osmol, solution B is 2 osmol, and solution C is 1 osmol. Notice how the osmolarity of solution A and C are equal. So solution A and C are osmotic to each other. Iso means the same. So the number of particles in solution A is exactly equal to the number of particles in solution C. If we compare solution A to B, solution A has less particles compared to solution B. So how do I say solution A has less? We refer to it as hypoosmotic. Hypo means low. What if we compare solution B to A? B has more particles compared to A, and so we refer to it as hyperosmotic. And so those are the terms that we would use to compare the number of particles between two solutions: isosmotic, hyperosmotic, and hypoosmotic. Tonicity is the term that we use to describe a solution outside of the cell. And how is that solution going to affect the cell volume if it was placed into that solution? Meaning, is the cell going to gain water? Is it going to lose water? Or is the water going to exit and enter the cell at an equal rate? But the thing about tonicity is that when we think of tonicity, we have to think about the concentration of what's known as non-penetrating solutes. An example of a non-penetrating solute is sodium chloride. Now, what does it mean that sodium chloride is non-penetrating? Does that mean it's not allowed to pass into or out of the cell? It is allowed. If you guys remember our intracellular fluid versus our extracellular fluid, sodium is located both inside of the cell and it's also located outside of the cell. But where do we have more sodium concentration? We always have a higher sodium concentration outside the cell versus inside the cell. it's much lower. We also have a higher concentration of chloride ions compared to inside of the cell. So why is sodium chloride considered non-penetrating even though we have it both inside and outside the cell, meaning that it is moving? The thing is, to maintain the higher concentration of sodium and chloride ions outside the cell, whenever sodium chloride enters the cell is going to quickly push them out. And that's why we refer to it as a non-penetrating solute, just because when they enter into the cell, they are quickly pushed out. What's an example of a penetrating solute? So glucose. So glucose usually goes into the cell and it's not going to be pushed out. And so we refer to glucose as a penetrating type of a solute versus sodium chloride would be considered a non-penetrating solute. The terms that we use to talk about tonicity are iso, hyper, and hypotonic, not osmotic, because we are talking about tonicity here and not osmolarity. With tonicity, again, remember, we are always going to be describing the condition outside of the cell and how that condition is going to affect the cell volume. So if the solution outside of the cell has the same amount of non-penetrating solutes compared to the cell, we refer to it as an isotonic solution. If the solution outside the cell has a higher concentration of non-penetrating solutes, we refer to it as a hypertonic solution. If the solution has a lower concentration of non-penetrating solutes compared to the cell, we refer to it as a hypotonic solution. So as I said, tonicity is going to describe what's going to happen to your cell. So let's say that you have three solutions, A, B, and C, and you went ahead and you dropped some cells in each one of those solutions. Notice how when you placed your cell in solution A, the cell swelled up. What does that mean? It means that the water moved into the cell. And the reason why the water moved into the cell, because solution A has a lower concentration of non-penetrating solutes. And remember when we talked about osmosis and we said osmosis always likes to go from the lower solute concentration to the higher solute concentration. And so we refer to solution A as being hypotonic because it has much lower solute concentration compared to the cell. So the water keeps moving into the cell and it will gain too much water that it can, to the point that it will swell and it actually might burst. Notice how in solution B, you went ahead and you placed your cell in solution B and nothing happened. It did not change. So what does that mean? It means that the water was able to enter and exit the cell at an equal rate, meaning that solution B is isotonic. It has the same amount of non-penetrating solutes in the solution and in the cell. When you placed your cell in solution C, the cell shrunk. And the reason why the cell is shrinking, because the water is actually exiting the cell. And the reason why the water is exiting the cell, what does that tell you? It tells you that solution C is hypertonic. It actually has a higher concentration of non-penetrating solutes in it. So one more time, with osmosis, the water likes to go from the low solute to the high solute concentration. And so the water in this case is going to exit the cell and it's going to be pushed into solution C where there's a higher concentration of solutes. I would like to talk about a 5% dextrose solution because it's usually used in IV fluids. So if you have a 5% dextrose solution, dextrose is glucose, and you want to figure out the osmolarity of a 5% dextrose solution, how can we go ahead and calculate that? So 5% meaning that you have 5 grams and 100 mils of solution. And so when you do the conversion into, how much is it in terms of grams per liter, it's basically going to be 50 grams per liter. And we know that 1 mole of glucose is 180 grams. How did I figure this out? Glucose is written as C6H12O6. So when you refer to the periodic table, and you go ahead and you find the weights of carbon, hydrogen, and oxygen, and you figure out the molecular weight, it's going to be 180 grams. So if you take your 50 grams per liter and each mole has 180 grams, that gives you 0.278 moles per liter. If you want to convert it into millimoles, you would multiply by 1,000, and so you would get 278 millimoles per liter. That's molarity. But if I want to go ahead and figure out osmolarity, as we said, you take your molarity and you multiply it by the number of particles. Glucose does not break down. And so all you would do is you would multiply by 1 particle because it does not break down, and you get 278 milliosmoles. Remember how we said the normal osmolarity in our cells is about 300? So you can round the 278 to 300, and so what does that mean? It means that the 5% dextrose solution is isosmotic to your cell, meaning that it has the same concentration of particles compared to your cell. So it's isosmotic. And why am I not saying isotonic? Because here we're talking about osmolarity and not tonicity. What's another type of solution that's usually used in IV fluids? 0.9% sodium chloride. So one more time, 0.9%, meaning that you have 0.9 grams of sodium chloride in every 100 mils of solution. And if you multiply that by 1,000 to think of it in terms of liter, it would be 9 grams per liter. 1 mole of sodium chloride is 58.5. Again, refer back to the periodic table, add the molecular weight of sodium and chlorine, and you will get 58.5. So if you have 9 grams per liter and each mole is 58.5 grams, that tells you that you have molarity of 0.15 moles per liter. Multiply that by 1,000 and you get 150 millimoles per liter. That's molarity. So if I want to figure out the osmolarity, you have to multiply by the number of particles. And we said sodium chloride breaks down into a sodium ion and a chloride ion. So that's 2 particles right there. So if you multiply 150 by 2, you get 300. What does that tell you? It tells you that a 0.9% sodium chloride is isosmotic to your cell. Because remember we said that inside of our cell, we have 300 milliosmoles. So let's talk about the different types of IV solutions that hospitals would hook up patients to. One of the IV solution regularly used at hospitals is a solution known as a 5% dextrose, which is glucose, in a 0.9% saline solution, which is sodium chloride. We know that inside of your cell, we have 300 milliosmoles. So let's figure out the osmolarity of that solution in that IV bag. A 5% dextrose is also 300 milliosmoles, and we just calculated it together. And a 0.9% saline is also 300. So what's the total of the osmolarity of that solution? It's a total of 600. Notice how that solution has way more particles compared to your cell? 600 versus 300. So how do I say that solution has way higher particles compared to my cell? Hyperosmotic. But if I want to talk about tonicity, am I going to be thinking about the total 600? No. With tonicity, you only think of the non-penetrating solute. So outside your cell, there are two solutes outside your cell. In this case, there's dextrose and there's sodium chloride. Which one is the non-penetrating? The sodium chloride is the non-penetrating. Why? Because as we said, dextrose is going to move into the cell. Sodium chloride is going to be left behind. Yes, it can enter, but remember how we said it's going to be pushed out. And so when you think of tonicity, only think of the 0.9% sodium chloride. 0.9% sodium chloride is 300. And that's the same as what you have inside of your cell. And so the thing is, that solution is isotonic. So if I'm thinking about the water movement, the water is going to be entering and exiting the cell at an equal rate. So usually they would hook up patients to that type of solution if they want to give patients some some caloric intake because it has some glucose in it, and they want to hook up that patient to that solution if they want to make up for some fluid loss. What's another type of IV solution that they usually hook up patients to? A 5% dextrose in water. One more time, your cell has 300 milliosmoles. And we know that 5% dextrose is also 300. Notice how equal amounts? So 300 and 300, that means that my solution is what? Isosmotic to my cell. Now we know that dextrose is a penetrating solute. So what's going to happen to dextrose is that it's going to start entering into your cell. Leaving what behind? Leaving the water behind. And so that means that if all the dextrose enters into the cell, you're going to end up with all of that water outside of the cell. And that means that the solution is going to be hypotonic. Because why is it hypotonic? Because now you have way more water outside the cell compared to inside. And so what's going to happen is that the water is going to start entering into the cell. They have to be careful when they hook up patients to those IV solutions because too much of it and the cell can start to take in too much water and swell up. And usually they give patients a hypotonic solution like this one if the patient is experiencing intracellular dehydration. What's another IV solution that's usually used at hospitals? A 0.45% saline. One more time, the cell has 300 milliosmoles. What is 0.5% sodium chloride? A 0.5% sodium chloride is about 150 milliosmoles. If you compare the particles, 150 compared to 300, you would notice that outside your cell there's way less particles compared to the inside of the cell. And so how do I say way less particles? Hyposmotic. So the solution outside the cell is hyposmotic compared to the cell. Tonicity would be hypotonic because normally we have 300 milliosmoles and outside now we only have 150. So 150 compared to 300, that's a hypotonic solution. So one more time, the water is going to start entering the cell and they have to be careful because the cell might take too much water, swells, and bursts. What's another type of solution that they can hook up patients to? A solution known as a 5% dextrose in 0.45% saline. We know that inside the cell there's 300. Let's go ahead and calculate the osmolarity of the solution outside your cell. 5% dextrose is 300. 0.45% saline is 150. So what is the total? The total is 450 milliosmoles. 450 compared to 300 inside of your cell is way more particles. So how do I say it has way more particles? We refer to it as hyperosmotic. But when I want to think about tonicity, am I going to think of the total 450? Nope, do not think of the total 450. Only think of the non-penetrating solute. So out of the two, dextrose and saline, which one is the non-penetrating? Saline. So when you think of tonicity, I'm only going to think of those 150 milliosmoles, not the total 450. And so now compare those 150 to the 300 inside of the cell. 150 outside is way less than 300. And so the tonicity is hypotonic. So one more time, if I want to think of what's going to happen to my cell, the water is going to be rushing into the cell because the solution outside of the cell is hypotonic compared to the cell. Notice how the solution outside could be hypotonic, but in terms of osmolarity could be hyperosmotic. So never assume that because it's hyperosmotic, it's going to be hypertonic. As you can see right here, that's not the case.